Thanks, Michelle. And thanks for the opportunity to present on this project, which has been absolutely wonderful to work on for the last 4.5 years. I'm not quite sure where the 4.5 years have gone because it's flown past. But we have managed to reach the end point that we were aiming for. The project was structured into 4 tasks, which Michelle will talk about tomorrow, so I won't go into the project details. I'm going to talk largely about the results and how they can be implemented and what they translate to in terms of the next steps for governments in particular. But the project has produced some absolutely wonderful outcomes as well as the core projections themselves, and the quality of those outcomes, I think, is worth stressing. It's the largest Goyder project and has produced 2 books, 35 journal papers, including 5 papers in the Nature suite of journals, 12 in the Journal of Climate, 5 in the International Journal of Climatology, and 1 in Geographic Research Letters. Those are all very, very top quality international journals. And the take-home message there, journals excite me, they probably don't excite you quite so much, but the take-home message is the work's all been peer-reviewed at the very, very highest level. So there is a high degree of certainty, if you like, about the academic rigour that's gone into the research. And therefore that translates into a high degree of certainty in terms of understanding the climate science. And my take-home message from this presentation is the next stage is to make sure that the governments involved take that climate science, which I think is probably the best science that's available in Australia, and we have it specifically for South Australia. The next challenge is to take that science and move it forward into adaptation, very similar to what Brian's just presented on. If we don't do that and the results sit on a shelf, then it's all been a waste of time. So that's the next key challenge. Why did we focus a project purely on South Australia when other work's been focused on much more broadly across Australia? The answer is we've got very unusual climatic conditions in South Australia. The map on the left-hand side shows the 8 NRM regions for South Australia, and the gradients you can see are the gradients of rainfall in the state. So you can obviously see a large north-south gradient, and everyone's familiar with the Goyder line, and the Goyder line has been demonstrated in this project is in fact drifting southwards, so it's not a fixed line as we are used to thinking about. But a great place to have located Adelaide would not have been Adelaide, it would have been 100 kilometres south in the middle of the ocean, because that's where a lot of our rainfall falls. And that's the big problem, the big challenge we're facing, is all of those gradients you can see are actually all drifting southwards, which means that the climate conditions that the northern parts of the state have been experiencing for the last 100 years are going to be experienced further south all the time. That's one reason that spatial variability is very important. But then let's focus in on the east-west translation. You might think in the state that's less so. The diagram on the right shows all of the 200 rainfall stations that we had available in this project, plotted longitude, latitude and rainfall, annual average rainfall. And you can see there's actually quite a spread going east-west as well, but it's not as defined, it's more clustered. But basically, the rainfall variability across the state is very high. If you want a really classic example, it's where we're sitting right now. Only 13-odd kilometres away, the rainfall is 1,200 millimetres, and just go the same 13 kilometres towards the coast, and it goes down to less than 500 millimetres. It's one of the steepest gradients in Australia. Wollongong has probably got a steeper gradient because of its topography, but Adelaide has one of the highest gradient rainfall changes of all the state capital cities. So that's a very important message. What affects our climate? There was a large part of the work that was conducted looking at what we call climate drivers or climate indices. And what affects the Adelaide climate is not the same drivers as what affects the Sydney, Melbourne and Brisbane climates. Some of the effects are the same. So the effects of ENSO are, in most cases, felt in both regions. But Adelaide's climate is, and I'd like to thank Wenju Chai for this slide and the next slide, is quite strongly affected, and the ENSO signal is moderated by the IOD, the Indian Ocean Dipole, which affects largely the western parts of Australia, including obviously Perth, but also Adelaide. If you want an example of that, the top diagram there shows the winter influence of IOD, the Indian Ocean Dipole. The winter effects of ENSO are shown on the middle diagram, and the combination of the two in spring is shown in that bottom diagram. There's been a lot of work that's come out of this project that has characterised those influences. When do they cut in? They don't happen all year long, and the influences on each other varies. And one of the big outcomes early on in this project was the move away from looking at seasonal variations in climate, winter, spring, autumn, summer, and working out that that's just not good enough. It's too coarse. We need to go down to at least monthly resolutions in order to see when those influences cut in and cut out. So, what does that look like? These are the 8 NRM regions with those signals. The top row is the SOI, which is a signal for the ENSO. The middle one's DMR, which is a single signal for the Indian Ocean Dipole. And the bottom one is another ENSO signal, which is NINO 3.4. And going vertically, it's June, July, August. And you can see that the SOI signal, I should say that the large red dots are at 1% statistical significance. That's incredibly high from a statistical viewpoint. The medium ones are at 5%. Oh, sorry, the smaller ones are at 5%. So you can see that the ENSO signal is very strong. Well, it's in fact quite weak in June, picks up into July, and carries on into August. The DMI, extremely weak in June, very strong in July, and retaining strength through to August. Whereas the NINO 3.4 is not having much influence at all on any of those stations. That was winter. This is for the 3 months of spring. And remember I said we've broken it down into the months rather than characterising it as seasons. Again, by September, the ENSO signal's weakened. The IOD signal has carried on strongly through to October, but then dies off in November. And the NINO 3.4, again, not much signal at all. How does that play out in terms of rainfall? These are rainfall trends at 1%, 5% and 10% statistical significance levels. And you can see that there's not a great deal of trend observed in winter and spring in the northern parts of the state, but in the southern parts of the state, particularly in winter, there are significant declining trends. Those stars are basically a decline in rainfall at very high statistical significance levels. Similarly in spring, the spring actually has quite a few positives in there, but the rainfall in spring in Adelaide is much lower than it is in winter. It's not such a good picture as it possibly looks. So moving forward to the projections, you're probably all familiar with how a GCM works. The GCMs, with the latest iteration, it is worth stressing that we were very pleased to be able to incorporate the latest CMIP5 models, which have only recently been released, into this project. There was always a plan to translate it and make it translatable in case they came out late, but they didn't come out late, and all of our projections are based on the very latest GCM models, the CMIP5s. This is a schematic of what a GCM looks like, and it picks up a picture. GCMs used to be called global circulation models for good reason. They're now called general circulation models, and it picks up the picture of the climate in the world, which is obviously very powerful. But that picture shows South Australia with a typical GCM grid superimposed. So you can see let's take, for example, the Onkaparinga catchment. Look how small it is. Look where it's situated between two nodes of the GCM grid, nodes number 8 and 5 in that picture. And if you wanted to pick it up from a straight GCM output, that's what you'd be looking at. There is not a single cloud that could be represented in that GCM output. The cloud structures are too small to be picked up by a GCM scale, okay? Which is why we don't do that, we downscale. And I'll show you how that works. Now, what about the variability? You'd get one set of outputs for node 5, you get another set of outputs for node 8. Onkaparinga catchment, situated roughly halfway between, has a gradient ranging from 1,200 millimetres to 500 millimetres at the coast. There's absolutely no way you're going to pick that up straight from a GCM, even if you could pick up the rainfall, which is unreliable in any case because of the scale. So how does that translate? That top graph there shows what I've just shown on the previous slide. And what we're going to look at now is two ways that we could have brought that down to the catchment scale. One way is to regrid it using what's called an RCM, a regional climate model. It's quite an expensive way of doing it, very time-consuming, requires an enormous amount of data, and generally, with today's capabilities, does not produce accurate enough results. The method we choose is the one that's internationally used most widely, which is statistical downscaling, where you take a series of predictor variables from the GCM and you create a predictand, which in most cases, in this case, was rainfall and a series of other predictands as well. Okay? And you downscale it to a point where you have got very reliable data, i.e. a rain gauge station. Okay? So we could statistically downscale to all of the stations, all the 200 stations that we had available where we had good data. And then you can compare the performance with the historical measurements as well as with the projected future climate. So that, in effect, is how our methodology worked. What did it produce? Well, I'm going to run through a series of slides now that Graham will be presenting on in more detail and more pictorially. So these are like a snapshot of the results. And Goyder Institute is in the process of producing fact sheets that capture some of these key messages. So in the Onkaparinga catchment, for instance, there's a significant increase in consecutive dry days. Adelaide already has the largest inter-event summer periods of any capital city. Statistically, it's about 7 days on average. The equivalent figure for Melbourne, which also has quite high inter-event dry periods, strangely enough, is 5.5 days. So we've already got 1.5 days more than the second longest, and that will increase into the future. That will have a huge impact on bushfires, potential bushfires, because our catchments will have longer to dry out. It will also have a big impact on vegetation change, because vegetation that requires regular watering will not survive in those longer periods. So there's a couple of impacts there. And Brian also mentioned the impact on soil moisture for agriculture. That will also, the soils will be drier, particularly in the summer periods. So very, very significant potential impacts on land use. The average flows will decline by 14% during the period 2016 to 2045, and by a further 37% by 37% in the period towards the end of the century. And that's with quite a low, what's called an RCP, representative concentration pathway, which basically describes how much greenhouse gas emissions we're putting up into the atmosphere. That's quite a conservative picture, and we're not actually tracking on that at the moment. We're tracking at quite a high RCP at the moment, so unless governments change practices, there's a reasonable chance that the flows will actually be half of what they are today. There's a 20% chance, in fact, that they will be half of what they are today. And that's going to impact our reservoirs. Remember, Onkaparinga changes from year to year because we have a diverse range of water supplies in South Australia, but you can use a rough figure of 60% of our water comes from that catchment. So if the inflow's half, we've got a major problem. And it's not going to be solved by desalination plants. Low annual flows associated with the droughts also appear to be quite sensitive to the changes in rainfall, and they're expected to decrease by 20% as well. So that's just one catchment. We chose that catchment because that was our case study catchment. We've got more data there than anywhere else. What about a community like Kangaroo Island? Well, they haven't got the benefit, they haven't got the luxury that Adelaide's got of a diverse water supply. They do rely on rainfall effectively. Their inflows to their Middle River Reservoir are predicted to decrease by between 26 and 31%. That will have a major impact on that community, on its ability to expand and its ability to even carry on with business as usual. And the overall trend is a reduction of runoff within this catchment will obviously therefore have significant impacts on water resource planning. Another example, which Graham will be talking about, the southeast of SA. This is more ecological in terms of the modelling. Middle Point Swamp is the water level in that swamp is predicted to fall by 1 metre over the modelling period, and by 2030 there's a moderate risk that it will actually not exist. The vegetation the lush vegetation that requires water at the moment will disappear and will be replaced by brackish herbland and exotic pasture grasses during that period. And so quite significant changes from an ecosystem viewpoint. And that's just a case study, if you like. A lot of the infrastructure that the government's investing in, such as the Torrens Road to River Torrens project, the SA Water's major reservoirs and treatment works, all have lifespans, and a lot of those treatment works, by the way, are coming to the end of their useful life and will require either upgrading or replacing soon. They have lifespans that are very long and are of commensurate timescale to the timescales we're talking about here. So one of the key opportunities, as I mentioned at the very start of this presentation, is that the government, when they commission these designs, when they look at infrastructure investment, that they insist that this data goes into those designs. They insist that we make these infrastructure pieces, these assets, resilient to climate change. There's nothing to stop that happening. The data is all there. It's just a commitment from the government that's required in order to ensure that we move from this very accurate climate science to climate adaptation. Very, very important. So the consequences, we did some modelling on the Torrens Road to, I said proverbial we there. The project did some modelling on the Torrens Road to River Torrens project, and quite a significant change over what would go into the design today. A fall of 3 metres in groundwater level and up to 6 metres for a high emissions scenario. That has to go into the design. If that's not factored in, there will be extremely expensive remedial measures required during the life of that project. And remediation always costs a lot more than upfront investment in the design. Similarly, with SA Water's reservoirs, there's more work to be done. This is extremely complex, looking at water quality in the reservoirs and treatment works. But the initial work that SA Water's undertaken has demonstrated that the models can understand or include the impacts of climate change on water quality and can inform investment decisions moving forward. So that's one government authority that's taking this very seriously. They're a partner in this project and are committed to using this data going forward. I'll finish with a slide on future changes of rainfall, because the story there is quite interesting. And this is looking at rainfall extremes, both ends of the spectrum. High intensity rainfall and no rainfall. And it's the latter, actually, that is more important in many respects for us. The graphs on the right are a bit messy, but they basically show what the average changes are for different GCMs. And most of them fall below zero, which means there's a decline, and you'd expect that. But one of them in particular falls way above zero, and that's the worrying one. And it's this one in this bottom corner. CDD stands for consecutive dry days. I did mention this before. These are the actual modelling results. And we're looking at changes of between up to 23% for a low emissions pathway, or up to 27%. Now that will change the nature of our vegetation. It will impede the government's plans to roll out green infrastructure in Adelaide. It will have to be factored into a lot of the designs moving forward. It will affect agricultural practices. It will probably affect land use. It's a very, very significant finding indeed. And it will certainly reduce potential runoff and affect the groundwater storage and ultimately, as I mentioned before, lead to quite significantly increased bushfire risks. So I'll leave it there, because Graham's going to talk about some of those projects, the modelling outputs in more detail. I'd like to acknowledge, obviously, the SA government for its very, very significant funding it's put into this climate change research, and I think the project has delivered what is probably the best set of environmental data available to any government in Australia. The challenge now is for governments to use that data. And I'd also like to thank Graham Pearman, Darren Ray and David Post for being a fabulous scientific advisory committee that's kept us on track throughout the whole project.